90 years ago, scientists believed that atoms were solid and indestructible particles like billiard balls. Our present knowledge of atom is totally different. Dear students, a number of experiments in the late part of 19th century showed that atoms are complex systems composed of a number of subatomic particles. Today we are familiar that atoms are principally composed of three fundamental particles: electrons, protons, neutrons. Today we shall discuss some of the important experiments that have led to the present idea of structure of atom. They are study of electric discharge through gases at low pressure, radioactivity, X-rays analysis, spectroscopic studies. Let's see in detail how the subatomic particles were discovered. Electrons were discovered by William Crookes. When he applied high voltage across the electrodes, he obtained a bright light glow on glass wall opposite to the cathode. The rays producing the glow were named as cathode rays, as these arose from cathode and moved towards anode. Later on, the particle nature of cathode rays was proved by experiments. Cathode rays have these characteristics. They travel from cathode to anode in straight line. When an opaque object is placed in their path, they cast a sharp shadow of it on the end of the tube. They increase the temperature of the object on which they fall. They are particle in nature. When an electric field is applied, they are deflected to the positive pole of electric field, suggesting a negative nature of these rays. It was also found that nature of cathode rays remains the same no matter which gas or substance is used. Thus, these were considered to be the fundamental particles of atom and were named as electrons. Now let's see what is the charge and mass of these electrons. J.J. Thomson, after several experiments, calculated the charge to mass ratio of these electrons. E by m is equal to 1.75 into 10 raised to power 11 coulombs per kg. R. A. Millikan determined the charge on electron by introducing tiny droplets of oil between two positively and negatively charged plates kept in a small chamber. He found that charge on droplets was always 1.6022 into 10 raised to power minus 19 coulombs or some multiple of it. E by m is equal to 1.75 into 10 raised to power 11 coulombs per kg. Mass is equal to 9.1096 into 10 raised to power minus 31 kg. Dear students, you know that matter as a whole is neutral. It means that there must be a positive particle which could balance the negative charge of electron. This positive particle was discovered by Eugene Goldstein. He used perforated cathode in discharge tube experiments. When a perforated cathode was used, a fluorescence or a glow was observed opposite to anode. It was due to rays flowing in direction opposite to the cathode rays. These rays were named as canal rays. Their motion to cathode showed their positive nature. The characteristic properties of positive rays are: these rays travel in straight line and are deflected by electric and magnetic fields in a way that reveals their positive charge. The ratio of charge to mass for these positive rays is considerably smaller than for electrons. The E by m ratio of the positive rays depends upon the nature of gas in tube. The positive rays are now called protons. The mass of protons is calculated to be 1.6726 into 10 raised to power minus 27 kg. Dear students, you may be familiar that some elements like radium and uranium are radioactive. It means that they emit radiations. When a radioactive material is enclosed in a lead block and one end is opened, it is observed that a beam of radiations comes out of it. If electric field is applied across it, it divides into three parts. The beam attracted towards positive electrodes is called beta particle. The beam attracted towards negative electrodes is positively charged and it is called alpha particles. The beam which remains undeflected is called gamma rays. Although the electrons and protons were discovered, Yet a problem was that mass of atom was twice as sum of mass of proton and electron. It meant that there must be some other fundamental particle in atom. In 1932, Chadwick discovered neutral particles in the nucleus. He bombarded nucleus of beryllium with alpha particles and found that it gave a highly penetrating radiations. This phenomenon of emission of radiation from nuclei of lighter atoms due to bombardment of moving particles is known as artificial radioactivity. These neutral particles were named neutrons. Dear students, when high energy electrons collide with anode, a very penetrating kind of radiation is produced. These are called X-rays. These are electromagnetic radiations with very high frequency. The number of positive charges on nucleus of an atom is called atomic number. It is denoted by Z. As you know that our present concept about atom consists of positively charged nucleus surrounded by negatively charged electron in orbits. The nucleus of an atom was discovered by Rutherford. Rutherford bombarded thin gold foil with alpha particles from a radioactive material. The alpha particle emerge from source at the left and strike on thin metal foil. Most of the particles go straight through foil. A few are deflected through various angles. He observed that the region which deflect the positive alpha particles must bear a heavy positive charge present in an atom. This part of atom is called nucleus. According to this model, an atom consists of a nucleus containing positive charge. The nucleus is surrounded by a number of electrons equal to the number of protons in the nucleus. The electrons are in constant motion. Now Professor Sharif will explain the atomic spectra.
Dear students, we have already explained Rutherford's atomic model. According to Rutherford's model, electrons are continuously moving around the nucleus in circular paths. If the electron moves in a circular path continuously, it should give off energy continuously and we should have got a continuous spectrum. When white light passes through a prism, it splits up into 7 different colors. The series of bands that form a continuous rainbow of colors is called a continuous spectrum. Since white light consists of radiations of all wavelengths, hence its spectrum consists of 7 colors and is a continuous spectrum. When light from the excited hydrogen atom passes through the prism, it splits up, but instead of forming a continuous spectrum, it forms lines which are separated by dark spaces, then lines separated by dark spaces. Such a spectrum is called a line spectrum, and since it is being given out by an element, it is called the emission spectrum. Here is the source, light is coming from here, here is our unexcited hydrogen, light passes through this unexcited hydrogen, then passes through the prism and gives us a spectrum which is seen here as lines. Dark lines separated by bright spaces. Such a spectrum is called absorption line spectrum. According to Rutherford's model, electron is continuously moving around the nucleus, and if it continuously moves, it should continuously emit energy. As you have seen, for all the atoms we get line spectrum. For continuous emission of the light, we should have got the continuous spectrum. To remove this defect or to explain this defect, Bohr he presented a model for the hydrogen atom. To Bohr's model, the total mass of the atom lies in a smaller part called the nucleus, and at a distance r from the nucleus there are electrons. In case of hydrogen, there is only one electron with mass me and it is moving with velocity v in circular path. When the electron is moving in a circular path, it should have angular momentum, and that angular momentum is mvr equal to nh over 2 pi, means angular momentum varies with the value of n by the factor h over 2 pi. Since the electron moves from in the fixed orbit, it does not lose or it does not gain the energy. However, when it moves from a lower orbit to a higher orbit, it shall absorb energy, and when it moves from a higher orbit to a lower orbit, it shall emit energy, and that energy is in the form of a photon of light. If energy in the second orbit is E2, energy in the first orbit is E1, then the difference delta is E2 minus E1 equal to h times nu, where h is Planck's constant and nu is the frequency of the light emitted. The electron does not fall in the nucleus, it does not leave the atom. Bohr suggested there are two kinds of forces, a centripetal force and a centrifugal force. Centripetal force is the force of attraction between the positive nucleus and the negative electron, and centrifugal force is force due to the motion of the electrons. Equating these two forces, then he calculated the radius of the atom, and radius for the hydrogen atom was calculated to be equal to 0.0529 angstroms. Using the same factors, he calculated the energy of the total atom. He said the total energy is energy due to potential energy plus the kinetic energy. From potential and kinetic energies, he calculated the total energy of the electron, which is equal to 2.18 times 10 to minus 18 joules times 1 over n1 square minus 1 over n2 square, where n1 is the orbit with lower energy, n2 is a higher orbit with high energy. 2.18 times 10 to minus 8 joules are the values of the charge on the electron, mass of the electron, the permittivity of the system in which these are to be calculated, and h is the Planck's constant. Now, when the electron moves down to n equal to 1, we shall show this from this picture. Here is a picture that shows the nucleus of the atom, and around the nucleus there are different orbits. Orbit number 1, 2, 3, 4, 5, 6, 7 are going to n equal to infinity. When the electron moves from any higher orbit, say 6, 5, 4, 3, 2 to n equal to 1, the spectrum that is given is called Lyman spectrum. It was calculated by a scientist called Lyman. Similar, and it falls in the ultraviolet region of the electromagnetic radiations and is a high energy spectrum. Similarly, when the electrons come from a higher orbit and stay in n equal to 2, the spectrum given is in the visible region, and such a series of lines is called the Balmer series, which was calculated by Balmer. When electron comes from n equal to 4, 5, 6 or 7 down to n equal to 3, this falls down in infrared region. In n equal to 3, n equal to 4, n equal to 5, all of these are infrared spectra, and the spectrum from a higher orbit to n equal to 3 is Paschen spectrum or Paschen series of the lines. From a higher orbit to n equal to 4, it is the bracket series of the spectral lines, and from n equal to 6 or 7 to n equal to 5, it is the Pfund series of the spectra calculated by Pfund. Dear students, now we shall explain the quantum mechanical treatment of the atom. Erwin Schrödinger, a German scientist, he suggested are all the particles which are of small size, they are moving in a wave form motion. In case of atoms, this wave motion is a circular wave motion, and they represented this wave motion by a wave function called psi. It is the square of the wave function, psi square, that gives the probability of finding the electrons, and he called that the orbital. The wave equation suggested by Erwin Schrödinger is a double differential equation. It took this double differential of the wave function psi along x axis, y axis and z axis. So, it is d2 psi over dx square plus d2 psi over dy square plus d2 psi over dz square plus 8 pi square m over h square into E minus V into psi equal to 0, where m is the mass of the electron, h is the Planck's constant, E is the total energy, or V is the potential energy of the wave of the electron. A solution of this equation is a very complex problem. It cannot be solved for complicated atoms, because in case of complicated atoms there are other forces besides the force of attraction between the positive nucleus and the electron. If there are more than one electrons, then there shall be a force of repulsion between the electron and between proton and the proton. Therefore, this equation was solved only for hydrogen and hydrogen like atoms. However, a very useful information about the position, about the shapes of the orbitals was obtained from this equation, and that is in the form of 3 quantum numbers. Among those quantum numbers, number 1 is the principal quantum number, which is represented with letter n, and it gives us the energy of the electron as well as the distance from the nucleus of an atom to the outermost shell. The nearest orbit or the orbital, that is s orbital, and the probability of finding the electron, if this is the distance from the nucleus and this is the probability of finding the electrons from the nucleus, the probability of finding the electron is maximum in 1s orbital, which is its shape would be like this. Okay, here is a nucleus, and around the nucleus there is a symmetrical space where probability of finding the electrons is same on all the sides. This was the shape of the orbital was calculated from the Schrodinger wave equation given by a second orbit quantum number called azimuthal quantum number. Azimuthal quantum number determines the shape of the orbitals and also contributes towards the energy of the orbital. So, according to the combination of these two, the principal quantum number and the azimuthal quantum number, we calculate the total energy of the electron. When electron is in 1s, it has the lowest energy. When it goes from 1s to a next orbit 2s, it has higher energy and probability decreases. Same way from 2s, then it goes to 2p. A p orbital is like a dumbbell. So, the dumbbell shall be either along x axis. If we have this p orbital, this is 2px, this is 2py, this is 2pz. The d orbital has 5 orientations to the applied magnetic field. Those are dxy, dyz, dzx, dz square, and similarly there would be one between dx square minus y square. If n is equal to 4, it shall have 4 subshells. Those are s, p, d and f. F can have at the most 14 electrons. These were the 3 quantum numbers which were obtained by the solution of Schrodinger wave equation. The 4th quantum number is the spin quantum number, is a defined quantum number. When electron is in the orbit, it moves either in clockwise direction or in anti-clockwise direction. The spin quantum number s, that is represented by the direction of the motion of electrons. It is represented either by an arrow pointing upwards or an arrow pointing downwards, or sometimes by plus 1.5. That means the electron is moving in a clockwise direction, minus 1.5 showing that electron is moving in anti-clockwise direction. Dear students, let us now see the configuration of a few elements. As you know, electrons would first go to the orbit of lowest energy. Hydrogen has only one electron, and that electron would go to the orbit of lowest energy, which is 1s1. Helium has 2 electrons, and s can accommodate 2 electrons. Therefore, both the electrons would go in 1s2, but these 2 electrons shall have their spins opposite to each other. One is clockwise, the other is anti-clockwise. In case of lithium, there are 3 electrons. Out of these 3 electrons, 2 would go in 1s and 1 electron would go in 2s. So, the configuration would be 1s2, 2s1, where this 1 represents the principal quantum number and this 2 and 1 represents the total number of electrons. In case of beryllium, we have 4 electrons. These 4 electrons are distributed, 2 electrons in 1s and 2 electrons in 2s. Both the electrons have opposite spins. The orbitals are completely filled here. Now, when orbitals of same energy level are available to the electrons, electrons would like to stay in separate orbitals with similar spins rather than to pair up and have opposite spins. This is called Hund's rule. Like in case of beryllium, we had a configuration 1s2, 2s2, but we had 2px, 2py and 2pz empty orbitals. The principal quantum number of 2s and 2px, 2py and 2pz is same, means their energy level is same. Therefore, an electron from 2s would like to go in one of the 3 2p's, leaving one electron behind and one electron in say 2px, 2py and 2pz still are empty. And we know beryllium makes 2 bonds. It can make 2 bonds only if there are 2 electrons in 2 unpaired electrons in the valence shell, and that is by using its internal energy an electron from 2s is excited into 2p. This is called Hund's rule, the shifting of electrons from a lower orbit to a higher orbit if it is of the same energy level. Dear students, the electronic configuration of an atom is a way to have an insight into the structure and the behavior of atoms. In the group 1, going from top to bottom, from lithium to francium, the number of shells are increasing, number of protons in the nucleus are also increasing, but the size of the atom increases more than the force of attraction between the protons and the electrons. So, we can say the size of the elements increases from top to bottom in every group throughout the periodic table. And as we go from left to right, the electrons are being added in the same outer shell. Say in case of lithium, we had 1s2, 2s1. In case of beryllium, we have 1s2, 2s2. In case of boron, we have 1s2, 2s2 and 2p1. Means the electrons are being added in this same shell, number of protons in the nucleus are increasing, the force of attraction between the electrons and the positive protons increases. As a result, the size decreases. Going from lithium to fluorine, the size decreases. Same way, going from sodium to chlorine, the size decreases. The arrangement of elements in this way, from top to bottom in the form of columns, are called groups, and from left to right, these are called periods. There are total of 7 periods and there are total of 8 groups. Elements are classified according to their electronic configuration. Elements of group 1 and 2 are called S block elements. Elements from group 3 to group 8 are called P block elements. Elements that are in the middle of the periodic table, these are all metals and their configurations end with d orbital.
Dear students, in this program we have discussed few aspects of atomic structure. Atom consists of 3 fundamental particles: electron, proton and neutron. Electrons were discovered as cathode rays and have a unit negative charge. Protons were discovered as canal rays and have a positive charge. Neutrons are neutral particles. The size of nucleus is very small as compared to the size of atom. Certain elements are found to emit radiations. This phenomenon is called radioactivity. The radiations emitted are alpha, beta and gamma rays. White light gives a continuous spectrum, while an element has its own characteristic line spectrum. Bohr model of atom explained radius, energy and spectrum of hydrogen atom. The region in space around nucleus in which an electron is most probably located is called an atomic orbital. The 4 quantum numbers help to decide energy, shape and orientation of orbital and direction of their motion in an atom. This program is about an introduction of the atomic structure. See you in next program. Allah Hafiz.